Today's topic is alcohols or alkanols. So what does it mean by alcohols? These are the hydroxy derivatives of alkanes. If you take an alkane, we know that this is a general alkane. If one of these hydrogen is replaced by OH group and we get ROH part, which is called as the alcohol. So alcohols are usually called as the hydroxy derivatives of the alkanes. So in today's session, let us see initially classification of these alkanes. Classification of alcohols. So alcohols are basically classified into two types. They are monohydric alcohols many are there, but I am taking two types. Okay, let us take some other type also. Monohydric alcohols, dihydric alcohols, trihydric alcohols, and polyhydric alcohols. So in this, let us take the monohydric alcohols. These alcohols are having only one OH group, and dihydric alcohols will have two OH groups in that particular molecule. Trihydric alcohols are having the three OH groups. And polyhydric alcohols are having the more than three OH groups. So these are called as the polyhydric alcohols. Now let us take the example of each and every of these categories. So first of all, monohydric alcohols. So these monohydric alcohols again of three categories. They are primary alcohols, secondary alcohols, and tertiary alcohols. In primary alcohols, the OH group is bonded to the primary carbon atom. In the case of the secondary alcohols, the OH group is connected to the secondary carbon atom. In the case of the tertiary alcohols, the OH group is bonded to the tertiary carbon atom. Dihydric alcohols, we said that two OH groups are there. You must remember one important thing that regarding the position of the OH groups, if two OH groups are placed on the same carbon atom, the molecule is unstable. So that you never try to place the two OH group on the same carbon atom. You have to place them on the adjacent carbon atoms or alternative carbon atoms wherever it is possible. So let us take an example. Best dihydric alcohol is CH2OH and CH2OH, which is called as ethylene glycol. Similarly, trihydric alcohol means three OH groups are present. So CH2OH, CHOH, CH2OH. So this is the trihydric alcohol, which is called the glycerol. And regarding the polyhydric alcohol, you can take any number of the OH groups in a particular molecule that is more than the three OH groups. Such type of the alcohols are called the polyhydric alcohols. Now you can see this molecule, how many carbon atoms are there? 1, 2, 3, 4, 5, 6. So the name of this molecule is sorbitol. It is having the 6 OH groups. This sorbitol is also known as the mannitol. Okay, and regarding the other category of the alcohols, that is allylic alcohol and benzylic alcohols also there. Let us see them also now. Allylic alcohol. We have already discussed what does it mean by allylic group. Allylic group means CH double bond CH single bond CH2. So sp3 carbon atom that is bonded to the sp2 carbon atom is called as the allylic carbon. So to this allylic carbon, if any OH group is bonded, that is called the allylic alcohol. So these allylic alcohols also again may be primary category, secondary category, or tertiary category. If you see, this is the primary allylic alcohol because this allylic carbon is connected to the only one carbon atom. And if you want to see for the secondary allylic alcohol, the molecule will be like this. This is the secondary allylic alcohol, and tertiary allylic alcohol is like this. So this is called like the tertiary allylic alcohol. Now let us see the benzylic alcohols. Benzylic alcohols. So in these benzylic alcohols, the OH group is bonded to the benzylic carbon atom. You must see that what does it mean by benzylic carbon atom. We know that this is the benzene to which a carbon atom is bonded. So the carbon bonded to the benzene is called the benzylic carbon. So this benzylic carbon, if it is having any OH group, that is called the benzylic alcohol. So this is the benzylic alcohol, and here also primary, secondary, tertiary are there. This is the primary benzylic alcohol, and this is the secondary benzylic alcohol, and this is the tertiary benzylic alcohol like this. Okay. So apart from this, let us see some isomerism also about these alcohols. As these concepts have been discussed, so that straight away I am explaining all these concepts. Much time I am not taking here because isomerism concept has been discussed in detail. You please check the notes. So isomerism, these alcohols show mainly three types of the isomerism. That is, first one is chain isomerism. So in the case of the chain isomerism, they have the same molecular formula and same functional group, but different the chain structure. So let us take the an example. Only one example I am taking over here. So in this case, this is the butane 1-ol, and whenever you are speaking about any isomerism, you have to take the two compounds. Then only it is called the isomerism. So in these two cases, molecular formula, number of carbon atoms are same. Four carbon atoms, hydrogens, OH2, everything is same. But here you can see OH group is connected to the CH2 group. Here also OH group is connected to CH2 group. Means no change in this one. But these two compounds differ only in their chain structure. Hence these are called the chain isomers. And second one is position isomerism. So position isomerism means OH group and the position of the OH group, functional group differs, but remaining everything remains same. So let's take an example of this. One example I'll take here: CH3, CH2, CH2OH, and CH3, CHOH, and CH3. So in this first compound, the position of the OH group at the first position, first carbon atom, but in the second compound, the OH group is placed on the second carbon atom. So they differ in the position of the functional group. Hence, these are called the position isomers. Now, let us see the functional group isomerism. So, functional group isomerism means here they have the same molecular formula. They differ in the type of the functional group present there. Generally, we know that alcohols and ethers are the functional group isomers. So just let us take a simple example. CH3, CH2, OH. This is ethyl alcohol where OH is the functional group and CH3, OCH3. Here oxygen is the functional group, means ether compound. So this is the alcohol, this is an ether. They are having the same molecular formula, 2 carbon, 6 hydrogens, 1 oxygen, but different the type of the functional group present in both of these molecules, and these are called the functional group isomers. So now let's come to the our main concept, that is methods of preparation of alcohols. Methods of preparation of alcohols. So let us check the alcohols, how to prepare the alcohols from different methods. The first one is from alkyl halides. Alkyl halides in the sense haloalkanes. So we know that haloalkanes and alkyl means preparation of the alcohols from the haloalkanes by using the SN1, SN2, SNA reactions we have already discussed. So I'll write here, alcohols are prepared from haloalkanes by SN1 and SN2 reactions using aqueous KOH or NaOH. So let's see some examples here. Just only this particular sentence is enough for you to understand how we are preparing the alcohols from the haloalkanes. Rest are just examples. Only use those examples for your practice purpose. So CH3, CH2, Br. So here we may use H2O OH minus. What does it mean by H2O OH minus? H2O means aqueous. OH minus means it is from the KOH or NaOH. So that you do not get confused is why we have used H2. H2 is nothing but in the place of the aqueous, they are directly using the chemical formula of that aqueous substance, that is water. So here this is the primary alkyl halide. Primary alkyl halide generally participate in what type of the substitution reaction, that is SN2 reaction. So that we get the CH3, CH2, OH, and let us take the another one, CH3, CHBr and CH3. Here this is a primary alkyl halide, this is a secondary alkyl halide. So secondary alkyl halides may participate in the SN1 reaction or SN2 reaction if you take the same substance, C, OH minus and H2O. If you write, you may write SN1 reaction and OH minus H2O and SN2 reaction depending on the conditions just. Generally, polar conditions preferable for the SN1 reaction, non-polar conditions for the SN2 reaction, but generally you can follow either SN1 or SN2 reaction, and finally the molecule will be same. Now, let us take the tertiary alkyl halide, CH3C, CH3 and CH3Cl. Now subject this molecule to the H2 is enough because it can easily dissociate this bond to form the tertiary carbocation. So OH minus is not required. Even the reaction carried will be carried out in the presence of the H2O. But anyhow, for more concentration of the OH minus, you can use it, or else not necessary. Generally, even in textbooks or in entrance examination, they are using like this only. So we know that SN1 reaction and CH3C, CH3 CH3OH. See, I am not discussing how many products are going to be formed. We know that here two products will be formed. Racemic mixture, concentration of racemic mixture, here Walden inversion, sent to Walden inversion. These are all. These discussions have been done in the SN1 and SN2 reaction. That's why here just only revising those concepts. Now let us see how to prepare the alcohols from alkenes. So alcohols preparation from alkenes. This we know that alkenes, if you take an alkene, just hydration of alkenes means add the water to the alkenes in order to get the alcohols. So for this particular concept, I had made a separate video just recently. You can see that particular video for more details and the mechanism of the getting how to get the alcohols from the alkenes. Here you can use the concentrated H2SO4 in the presence of the H2O, so that you will get the R, CH, OH and CH3. Here carbocation is the intermediate and rearrangement takes place. And in this particular case, you take the mercuric acetate HgOAc taken twice, NaBH4, H2, H2O, OH minus NaBH4. These combinations, and here also you will get the same Markovnikov type product and no carbocation, no C plus, no rearrangement. Now let us take the Diborane concepts B2H6 or BH3 with in the presence of the solvent THF, use the H2O2 OH minus, and you will get the anti-Markovnikov's product here. So this is the anti-Markovnikov's product. So I request you, if you don't understand this particular concept, how these molecules are coming, I request you please watch the hydration of the alkenes video, where I had discussed complete examples with the mechanisms. Whenever you want, you can watch it. Now, how to get the alcohols from Grignard reagent? Preparation of the alcohols from Grignard reagent. Generally, Grignard reagent reacts with the many functional groups. So Grignard reagent RMgX is called the Grignard reagent. It may react with the aldehydes and ketones and ethers, acid chlorides, not ethers, esters, epoxides, cyclic ethers are called the epoxides, even oxygen also, with oxygen. So RMgX reacts with all these compounds, gives alcohols. So remaining what I am going to discuss is just examples. This is the main concept of this particular Grignard reagent, how it is going to give the alcohols. Now let us see the how means Grignard reagent when react with the different compounds, you will get the different type of the alcohols. But mainly you will get the alcohols. Let us see what type of alcohols it is going to be produced. Mechanism I am not discussing over here. Just see RMgX. Okay. So this is Grignard reagent on reaction with the formaldehyde followed by H plus. This is second step actually, H2O. So this particular alkyl group will attack over this carbonyl compound. This carbonyl compound anyhow having the two hydrogens, so it becomes RCH2. These pi electrons will shift over there, and later this H plus N will attack here. So we get the R CH2OH. And let us take the another type of the aldehyde, CH3, C double bond O, H, H plus H2O. I should not write this H plus H2O together because this is the first step, this is the second step. Everywhere like this only. So now this Grignard reagent will attack over here. So it makes the R carbon bond. This CH3 already there. This carbon is having one hydrogen, and this double bond O becomes the OH. Means we are going to get the R C OH. This carbon is having one hydrogen. Later CH3 group is present. Now you just take the ketone. Ketone in this sense, let us take a best example, that is acetone. This is the one of the important reaction of the Grignard reagents. I'll tell you how and why. Here again, here it will attack and replaces this pi bond, so that here we get the R. Carbon bonds we are not breaking, we are making the carbon bonds. So this carbon already having the two CH3 groups, and new carbon bond is coming R, and finally it becomes OH. So one important thing of this particular reaction, anyhow this mechanism of this reaction will be discussed in the aldehydes, ketones and carboxylic acid lesson. Now the important thing here is Grignard reagent on reaction with the formaldehyde giving the primary alcohol. Rest of the aldehyde, you take any type of the aldehyde with a Grignard reagent, you will get the secondary alcohol, and the Grignard reagent with the ketones gives the tertiary alcohol. This is the important one that has to be remembered. Next, what about the acid chlorides and all this? Let us continue the same concept here with the anyhow we made this one, no? So let us extend this one with acid chlorides, RC double bond OCl. So here actually initially one Grignard reagent will attack, removes this chlorine. So what we'll get, anyhow I'll make a separate one. Why? Because a little concept regarding the mechanism is required. Okay, now you check here. I'll take the RMGX Grignard reagent, R dash I'll put here, and let us take the RC double bond OCl. Grignard reagent carbon always attacks over the carbonyl carbon, removes this chlorine in the form of the Cl minus. The Cl minus combines with the MgX. If it is MgCl, it will form the MgCl2. So later what we get are double bond O R dash. But still this is a carbonyl compound. So there is a chance for the one more Grignard reagent to attack. So again it attacks over here and replace this pi bond, so that we get the RCOMgX. Here R dash, here also R dash. Next, this is the step where we are using the H2O and H plus. So break this bond and we get the RCOH, R dash and R dash. So this is a tertiary alcohol. So acid chlorides on reaction with the Grignard reagent, they are giving the tertiary alcohol. So how many moles of the Grignard reagent is getting reacted with the acid halides? 2 moles of the Grignard reagent. Now let us take the esters. R C double bond O R dash. Here also this is the one leaving group like a chlorine here. So that one Grignard reagent initially attacks over here and removes this OR part. So we get the RC double bond O R dash, just like here. Again we need the help of the one more mole of the Grignard reagent to be attacked over here and to get the RCOMgX. Here R dash, here also R dash, and later last step is H plus and H2O. It breaks the bond like this. So ROH, R dash and R dash. Means both acid chlorides as well as the esters on reaction with the 2 moles of the Grignard reagent, they are giving the tertiary alcohol. If only 1 mole means they give the ketones. So this is the ketone step. Anyhow, this video will be shared to your email ID. Just check over there whenever you want to revise the concept. So RMGX Grignard reagent on reaction with the epoxides. Epoxides are nothing but the cyclic ethers. So negative part always attacks from the backside of this one carbon to open this ring in the presence of the H plus and H2O. So we get the R part will be connected over here. Next here OH. So these two will be in the opposite position. Okay. So after opening of the epoxide, Grignard reagent is giving the alcohol, but the type of the alcohol depends on the type of the groups present in this particular position. If two carbons are present, it will become a tertiary alcohol. If hydrogen and carbon, it will become a secondary alcohol. Both are hydrogens means it will be a primary alcohol. Depends on the type of the epoxide we select. Next, Grignard reagent even reacts with the oxygen, so to form ROOMgX. This one on reaction with the simple hydrolysis breaks the bond and giving the alcohol, and magnesium gets the one oxygen with the OH part, next one halogen. Means this water splits up into H and OH part. Okay, so that we get the two different particular parts. So alcohol we are getting whenever the Grignard reagent reacts with simply oxygen. So these are the reactions of the Grignard reagent or the formation of the alcohols using the Grignard reagent. Now let us see how to get the alcohols from the primary amines. It's one of the important reaction from primary amines. This is one of the important reaction. I'll tell you why this reaction is so important. Because people get confused of the reagents using in this particular primary amines. You must remember one small thing, that this is the main concept of this reaction, primary amine or reaction with the HNO2. This can also be written as NaNO2 plus HCl, constant HCl. It is in situ reagent, HNO2. In situ reagent means the reagent is prepared during the course of the reaction. We add both of these, we don't add HNO2 as HNO2 is an unstable compound. So primary amines on reaction with the HNO2, they convert this primary amine part into the alcohol. It is so important reaction because secondary amines gives different taste, tertiary amines gives the different taste with the HNO2. That we shall discuss in nitrogen contained compound, but still then just remember that primary amines wherever HNO2 is added, they give the alcohols, not other compounds. So I'll take some examples regarding this particular molecule. So you can remember these examples as simple examples I'll pick up. So NH2, you just add HNO2, so it gives CH3 CH2OH, primary alcohol, and you take this one also CH3NH2. NH2 is the primary amine, not NH. So use the HNO2, so that CH3 CHOH and CH3. You must remember one thing, that no rearrangement is taking place during the course of the reaction, and means wherever NH2 part is there, you remove that NH2 part, just put OH. HNO2 nitrous acid. These are all different examples from for which you just understand, try to remember these examples. So these are all the alcohols preparation from using the primary amines. Now let us see how to get the alcohols from ethers. Preparation of the alcohols from ethers. It's just very simple reaction, that ethers, you take any ether, this is the functional group of the ether, subject this ether to the acid hydrolysis, add H plus H2O, or else HBr, or else use HI also. Any of these combinations, you get the alcohols. If you use H plus and H2O, you get both are alcohols. If any of these two reagents, you will get the one as the alcohol, the second one as the alkyl halide. So this X may be bromide or iodide part. Okay, depending on the type of the reagent you select. Now let us take this some examples of this particular concept. CH3O C2H5H plus H2O. Take the means to break this bond, both will become the alcohols only. So this is the methyl alcohol, and the second one is the ethyl alcohol. Now let us take the another one. Use H plus and H2O, OH plus CH3OH. Now I am not discussing these certain reactions regarding the HBr and HI. The detailed discussion of these reactions will be done in the ethers concept because they give the different products. The question is about which alkyl group will be converted to the alkyl halide and the which one will be converted to the alcohol. So that mechanisms, everything will be discussed in the ethers lesson. So just here I am giving an example, and here no difference because just you have to break the bond and put the both convert them both of these alkyl part that are connected to the oxygen as the alcohols and use the H plus and H2O. So now let us see the from esters. So how to convert the esters into the alcohols? It's simple thing that hydrolysis. You take ester, this is a general ester, simple hydrolysis, H plus H2 acid hydrolysis. So it becomes the one part becomes the carboxylic acid, the other part becomes the alcohol. So which part becomes the alcohol means the carbon that is connected to the oxygen becomes the alcohol, and C double bond O group part becomes the carboxylic acid. Okay. Now let us see here. Cyclic esters also you can take normal esters, different categories. Let us take here now. This is one cyclic ester. So this cyclic ester is subject with the H plus and H2O. So where to break the bond? This area you break the bond. So it becomes the COOH, and this one becomes the alcohol. Even this compound is very unstable, immediately react with each other and they form the ester back. Okay. So like this, esters reacts with the hydrolyze in the presence of the H plus H2O. Even you can use the OH minus also, but mechanisms will be differed in the case of the OH minus. The mechanisms again we will discuss in the case in lesson carboxylic acids. Here I am just introducing all these concepts. How to get the alcohols, and indirectly we are introducing the properties of these particular functional groups. Means esters on hydrolysis gives the carboxylic acid and alcohol. Ethers they give the alcohols. Means how we are getting the alcohols from different functional groups. It is nothing but the chemical properties of these functional groups. So once you read one particular lesson and after half of the organic part you complete, then remaining is nothing but the revision of that earlier concepts. Now we are entering into one of the important and logical concept, that is how to use the lithium aluminium hydride and sodium borohydride. I want to make a separate video on this. Anyhow, here I will discuss and again I will make a separate video. So here lithium aluminum hydride and sodium borohydride both are the strongest reducing agents. They reduce in the presence of the H plus or H2O. So the reagent, both of these reagents, they deliver H minus ion to the functional group. You must remember that, to the carbon of the functional group. Means H minus ion, whatever is coming from both of these reagents, will be added to which one? Carbon atom, not to the other atoms. Only carbon atom of the functional group. and later H plus ion protonation happens. This H plus ion comes from the water, and this H plus ion will be added to the other atoms other than carbon atom. So let us discuss the important thing of both of these reagents. The important thing is, first of all, lithium aluminum hydride, which is the strongest reducing agent. It reduces many of the functional groups. Sodium borohydride is a selective reducing agent. Selective reducing agent means sodium borohydride do not reduce all the functional groups. Particularly, I will discuss here aldehyde, keto, and acid chlorides. So, sodium borohydride reduces only these three functional groups. You must remember, it will not affect other functional groups. H plus H2. So, sodium borohydride reduces all these functional groups to their respective alcohols. If you take the aldehyde, you will get the primary alcohol. If you take the keto group, you will get the secondary alcohol. And if you take the this particular acid halide, here also you will get the primary alcohol. So C double bond O group will be converted to the CHOH group. Then what about the lithium aluminum hydride? Lithium aluminum hydride reduces a vast number of the functional groups to alcohols. See here, aldehyde. You have to remember these reagents: ketone, carboxylic acid, ester, acid chloride. It reduces all these functional groups to alcohols. Which one? Lithium aluminum hydride. And apart from these reagents, you can include cyanides. With lithium aluminum hydride, it converts this one into the CN is there, no? So it becomes CH2 and H2. So primary amines. So I'll write at the functional group itself directly so that you can understand. R CH2 NH2 primary amines. It converts nitriles to the primary amines. At the same time, it converts the nitro groups to the RNH2. This is also primary amine, and it converts the alkyl halides to the alkanes. A different type of the reagents means, even here I forgot to mention that, means carboxylic acid and its derivatives. In this derivatives I forgot to mention the anhydride. Anhydride also will give the alcohol in the presence of the lithium aluminum hydride. And if you take the amide, C double bond O and H2, so this will become the primary amine. So you see, these are all primary amines, not the secondary amines. Only primary amines we are getting in this particular when use the lithium aluminum hydride. So I will take these some examples where you can easily understand the difference. But this is the main concept. Means aldehydes, ketones, acid chlorides will be converted with respect to alcohols when use the sodium borohydride. But lithium aluminum hydride, which is the strongest reducing agent, has the more spectrum so that it can convert the more number of functional groups into their respective products. Let us see one by one. Everywhere I'll compare the sodium borohydride with the lithium aluminum hydride. So, first example, let us take the aldehyde. Here you can take the lithium aluminum hydride or sodium borohydride, because both can reduce aldehyde to the their respective alcohol, primary alcohol. Now let us take the keto group, R dash. So here also you can use the lithium aluminum hydride or sodium borohydride. So both will reduce this keto group to their respective secondary alcohol. And the third one, let us take the acid chloride, H3COCl. Here also you can use the lithium aluminium hydride or sodium borohydride, which will reduce this acid halides to their respective alcohol. So up to here everything is same, but from now onwards the combination changes. We take the fourth one. Now if you take the RCOOH, which is the carboxylic acid, only lithium aluminium hydride, LaHL, right? LaH is nothing but lithium aluminum hydride. It converts the carboxylic acids to its respective alcohol. And let's take the RCOOR, R dash. This is ester, lithium aluminum hydride. So it disconnects this bond. It becomes this also CH2OH. This also becomes the alcohol. So RCH2OH plus R dash OH. And sixth one is you just take the acid anhydride, RC double bond O, C double bond O, R dash. Breaks the bond somewhere here. So lithium aluminum hydride converts this, because if it is C double bond, each C double bond will be converted to CH2OH. So CH2OH. So you will get the RCH2OH plus R dash CH2OH. Irrespective of the type of the alkyl group, its main duty is to convert all them into their respective alcohols. And the seventh example is RC double bond O NH2. So here lithium aluminum hydride converts them into the RCH2NH2. And eighth example is you just take the RC triple bond N, use the lithium aluminum hydride. Everywhere hydrolysis is required, so that you convert this one into the RCH2NH2. Now ninth one is you just take the alkyl halide, use the lithium aluminum hydride, you will get the alkanes. And so like this many functional groups, even nitro group not discussed here. So RNO2, L lithium aluminum hydride. So this shall be converted to the primary amine. Means in these particular reactions, if you observe one thing, that only for first three reactions we used both of these reagent, lithium aluminum hydride and sodium borohydride. But for rest of the reactions, we did not use the sodium borohydride. We used only the lithium aluminum hydride. So this reaction is so important for us that if multiple functional groups are present in a particular molecule, you can select the reagent, what type of reagent you want. Okay. And interestingly, lithium aluminum hydride, if you take any ether, lithium aluminum hydride, no reaction. So ethers are not reduced by the lithium aluminum hydride. Now I'll select some reactions. One reaction like this. Two ether groups are there, CH3, OCH3, and here OOCH3. And I want to reduce only this particular part. This is nothing but the ester part. These are the ethers. Ethers are not reduced by the lithium aluminum hydride, but lithium aluminum hydride can reduce this particular ester to the alcohol. But if you use the sodium borohydride, it will not affect any of these reagents, functional groups. Sorry, OCH3. So that this is a CH2OH plus CH3OH. Now here I had given one important point, that is H minus ion that is coming from the lithium aluminum hydride and sodium borohydride will be connected to the carbon atom, and H plus ion from the water is connected to the other than carbon atom. Okay. So in these particular cases you see C double bond OH actually. Aldehyde means C double bond OH. This has been converted to the CH, H and OH. So carbon is get added with the two hydrogens. and this oxygen is added with one hydrogen. So this hydrogen came from the water. So this is from the water, and these two hydrogens are from the lithium aluminum hydride or sodium borohydride. You must remember that. So for that purpose, I am giving the one important reaction to you all to understand. So I'll take this example to make you more understand about this concept. See, this I have taken. Now use the lithium aluminum hydride and D2 deuterium oxide. So lithium aluminum hydride gives the hydrogen H minus ion, hydride ion. That hydride ion has to attack over the carbon of the functional group, not on the oxygen. So that hydrogen comes here and O minus will be there, and this O minus has to get the proton from what? Water. So that we'll get the OD like this. But next time use lithium aluminum deuterate, means instead of the hydrogens use the deuterium. Now use the H2O. So actually lithium aluminum hydride is giving the deuteride is giving the D minus ion. D minus ion has to attack over the carbon atom of the functional group. So that here D will come, and O minus will be there, no? So that O minus will get the hydrogen from the water. So that OH. So this is the main difference of this particular reaction to understand you, to make you understand. Now I'll take different examples to make you fully understand about the sodium hydride uses and this lithium aluminum hydride uses completely. You just see this particular beautiful example where we are using this keto group is present, as well as the C double bond O C2H5, means keto group as well as the ester group both are present. If you want to reduce both of these reagents, both of these functional group, then which reagent you have to prefer? That is lithium aluminum hydride first of all. Second one is always followed by H plus and H2O. Without this one, it cannot complete the reaction. So it will reduce both of these functional groups. This keto group will be to the alcohol, and here it will be to the CH2OH, and this C2H5 also will be converted to the C2H5OH using the lithium aluminum hydride. Now I want to reduce only keto group. I do not want to affect this particular ester group. So in such cases, preferably I have to select the sodium borohydride, and second one is followed by H plus and H2O. So that what happens here is only this will be formed and this is unaffected. You know the reason, because sodium borohydride affects only aldehydes, ketones and acid halides, not the other functional groups like ethers, esters, whatever it may be, so that it will not be affected. Okay. Now you may ask the question, sir, here about the aluminum deuteride he had explained, then what about the sodium borohydride? Same concept. Here you can use the sodium borohydride also instead of NaBH4, and D2O is common for both of these. Means H minus is coming from both of these reagents will have connected to the functional group carbon like this, and here use the NaBD4. So that separate reaction is not necessary. D minus will attack over there. Okay. Now I'll take one more example. So in particular example, this is an example. Now when it is subjected to the, so here we use the lithium aluminum hydride, and here we are using the sodium borohydride. Second hydrolysis H plus H2, everything is common. H plus H2O. Here also H plus H2O. So you can easily expect the reagents, means products. That means lithium aluminum hydride converts only, this is the keto part, this is the aldehyde part. Sorry, lithium aluminum hydride can reduce all these parts. all these functional groups. But sodium borohydride affects only aldehyde and ketone, not the amides. So in this particular case, when lithium aluminum hydride is used, so it becomes alcohol here, and here also it becomes the alcohol, and here also it becomes the directly NH2 part, because this is not the NC alcohol, it will be reduced to the primary amines. But when sodium borohydride is used, what is the main property of the sodium borohydride? Reduce only carbonyl compounds and the acid halides. So keto group to the second alcohol, and aldehyde to the primary alcohol, and this particular amide is unaffected. So this is the main use of the both the sodium borohydride and lithium aluminum hydride. You have to remember these examples. This is a beautiful one for you. So you keep on watching this video repeatedly, because it will be shared to your email ID to fully understand these reagents whenever you want. So this is an important video for you all. Next, let us take one more also. What is the use of the diborane? BH3 or B2H6. So how this particular reagent is helpful in getting the alcohols? It is very simple, that it mainly reduces the carboxylic acids and esters. This is all selective reagent. So wherever carboxylic acid and esters are there, only these two reagents will be converted to the respective alcohols by diborane BH3. Whenever you are using the BH3, you have to use the THF, followed by H plus, and H2 is common in lithium aluminum hydride, sodium borohydride, and diborane everywhere. Okay, so its main selective reducing property is only to reduce the carboxylic acids and esters to the primary alcohol, and it will not reduce other functional groups like carboxylic RCOCl, acid halides, and all these will not be reduced. Okay, for example, I'll take one example here. This is an example. I want to reduce only this particular ester to the alcohol, not this acid halide. If you use the lithium aluminum hydride, it will reduce both of these. If you use sodium borohydride, it will reduce acid halide, not the ester. But I want to reduce only this one. So this one I shall discuss separately, which is a beautiful example for us. Use lithium aluminum hydride, H plus and H2O. So you know the products very well. So this is OH plus CH3OH, and this is also OH. And if you use the sodium borohydride, H plus and H2O, sodium borohydride reduces only acid chlorides to the alcohol and will not affect the ester. But if you use the B2H6 diborane, that means BH3, its monomer THF, H plus and H2O. So it reduces only this ester part, will not affect the acid halide. So you must be very careful in selecting the reducing agent based on the type of your requirement. That's why I told you this video is very important for you all. Fully understand the concept. And I'm going to give some examples for homework purpose also. So find the major product in the following compounds. HgOAc taken twice, H2O, NaBH4, OH minus. And second one is, answers will be discussed in the next class. Cl aqueous KOH. Third one is BH3 THF H2O2 OH minus. And fourth one is C bond O C2H5. Now I am using the lithium aluminium hydride, means previous concepts also, just I am including here. And fifth one is pH CH2 C double bond O CH CH3 CH3 H plus and H2O, this is. And sixth example, let's take the benzene OCH3 H. Anyhow, this reaction I shall discuss separately. So this is the homework for you. Dear students, hope you understand my explanation. If you understand my explanation, please like the video, share the video, and subscribe the channel. Thank you.